Bitch, don't kill my vibe. Bitch, don't kill my vibe. I can feel your energy from 2 planets away. I got my drink, I got my music, I would share it, but today I'm yelling, bitch, don't kill my vibe. Bitch, don't kill my vibe. Bitch, don't kill my vibe. Bitch, don't kill my vibe.
Hello everyone. Topic of this video is electric current. And as most of you probably know, electric current is movement of charge. It can be electrons or some positive ions or protons, whatever. And usually electric current is noticed or found in conductors. Let's say we have a piece of copper cable here. The fact that makes most metals good conductors is that they have, or the electrons in the copper atoms are free to move around when they're structured into a solid copper, like here. So here we have a bunch of electrons. But how do we make these move? So they have electric charge, so the best way to move electric charge is to have electric field. So let's say we have some positive charge on this side and negative charge here on the other side. So as you know, there's going to be an electric field going from plus to minus. And these electrons will see the electric field and they will be attracted towards the positive charge. So what happens in this case when there's no contact between the source of the field and the conductor? We will get a situation resembling something like this. Positive here, negative here. All the electrons, not all of them, some of the electrons will migrate towards the positive charge, so we have a bunch of electrons piling up on this side, and then on the other side the positive charge will tend towards the negative electrode here. So we have the external field going this way, so this is E external, and now because we have this distribution of charge inside the conductor, there would be internal electric field. And what happens here, these charges will start piling up until the electric field inside the conductor will exactly cancel the external field. So then the field disappears or is nullified in effect, and no charge can move anymore. This is exactly the case that we've been studying so far, the electrostatic case, where there is no field inside the conductor because the charge distribution in the conductor cancels whatever the outside field is. But this situation changes when we allow the conductor to touch the electrodes. So instead of having this parallel plate capacitor kind of a thing, we will connect our positive and negative terminals by the conductor. Now the field is there. This is the external field, and the electrons are attracted going this way, and they will, as before, they will start piling up on this side. But now if we can do something here, that we can collect the electrons from the positive electrode and on the other hand keep feeding them in from this negative electrode, the electrons, they don't start to pile up in any particular point in the conductor, but they will keep flowing as soon as we can collect them from here and keep feeding from here. Therefore, there will be no internal field in this conductor that would cancel the external field, and these charges, electrons, will keep flowing as shown in the figure. This collection and feeding can be realized by using a voltage source, for example, a battery. So battery this is the symbol of a battery, so it has positive terminal and the negative terminal. So let's say we would call this one to be 0 volts here, and this would be 12 volts. Now we have this potential difference across the connector that generates the field and keeps driving these electrons around the circuit. Electrons always are attracted to the positive terminal, so the electrons will flow this way, as shown in the figure. But in fact, the convention is that the current is in the opposite direction. Convention says that current will always flow from positive to negative terminal. And this would be true for positive charges. Remember, current can also be flow of other charges. It don't have to be electrons. But when we're dealing with electric circuits, the charge carriers are electrons, and they will always be attracted to the positive terminal. So this is the direction of the actual electron current. Whereas this would be called the conventional current. So the convention is the positive current is from positive to negative, but the actual direction of electrons is in the opposite. So once again, positive current is from positive to negative terminal. Electric current is denoted by symbol I, and it is measured in amperes. So the units would be amperes. And the actual definition of electric current is how much charge, delta Q, flows past some point in time delta T. So here's our conductor. So we can have an imaginary boundary here. And then we just count how many charges cross this boundary in a given amount of time. So the units of this one would then be coulombs over second, which is the ampere that I just mentioned. And here's an exercise demonstrating how we use this definition. So the question is, if 1 million electrons per second pass a point in a wire, what is the current in amps? Amp means ampere. So the current is amount of charge flowing past a point in given time. So the amount of charge can be expressed as number of electrons, called N, and the charge of an individual electron, Ne. So in fact we take the absolute value because charge of an electron is negative, but when we're talking about current, we just want the magnitude here. So number of electrons times the charge of one electron, and then the delta T, which in our case is 1 second. So let's plug in the numbers. N, 1 million, 10 to the 6. The absolute value of electron charge is 1.6 times 10 to the minus 19 coulombs divided by 1 second. So we get 1.6 times 10 to the minus 13 amperes, which is quite a small current. It would be 0.2 picoamps. It is still measurable, but it's tiny. So in order to have a significant current, we need many more electrons than 1 million per second.
That my city found me, then put me on stages. To me, that's amazing. To you, that's a quick check with all disrespect. Let me say this, say this, say this. I am a sinner who's probably gonna sin again. Lord, forgive me. Lord, forgive me. things I don't understand.